Hey, my name's Errol, and I'm the head of education here at Aleo. In this video, I want to demonstrate how cryptographers can prove that they know anything through the use of something called a Rank-1 Constraint System, which is a type of proof system. Examples of this are Marlin and Groth 16. Proof systems are very complex. There's a lot of moving pieces. So in this video, we could only cover some of the core ideas. But for the future, we're looking forward to making many more videos that break down the other core ideas involved in proof systems. We think this is really important because there's a lot of wealth being put on top of these technologies. And if you're going to do that, it makes sense to try and understand the technology a bit better, not only so that you can have more faith and trust that things are functioning as they should and that they can't go wrong, but also to be able to use the technology more effectively. If you understand how it works, it's going to be easier to creatively come up with ideas about how to exploit its value and derive this value for everybody. This walkthrough is primarily based off of a very popular blog post written by Vitalik Buterin, where he talks through an R1CS system using a specific example. And we use that example as well. So this is largely based off that. It would be very valuable if you can check through the article alongside this video if you have time. Let's introduce the equation that we want to prove knowledge of. We have x cubed plus x plus 5 equals 35. So what we're going to want to do here is prove that we know the answer to this equation. We know some value x that when you plug it into this format, it satisfies it. This particular equation came from nowhere. It's just a dummy equation, a toy example. The important thing is actually that you'll be able to turn any computer program into a set of equations like this. That's called the arithmetization. We don't really have time for it now, but if you think about it, it kind of makes some sense. Like, computers just ones and zeros moving around NAND gates. So why not bigger integers going through addition and multiplication? Won't that kind of be the same thing? The first thing we have to do in this process is something called flattening. We need to turn this equation into its fundamental steps. And when I say fundamental steps here, we're just talking about addition and multiplication, only in one go. So for example, the first item, x cubed, well, cubing is just multiplication, but we can't cube in one go. We're going to have to break it down to the steps. So the first step is going to be x multiplied by x, and this is going to give us x squared, but I'm just going to call it int here for intermediate, because if someone wants to fake a solution, they may put in the wrong value. The next is intermediate 2, which is x squared multiplied by x. Then we have int 3, where we're going to want to take x cubed and add x to it. Finally, we're going to want to add 5. In general, there are two types of operations we're allowed. The first is y equals x, so some parameter just equals the value of another parameter. And the other is that y equals x, some operation z. And really we're only expecting addition and multiplication here. And you can see that our first two constraints are of the form y equals x multiplied by z, and our second pair of constraints are of the form y equals x plus z. The next step is to actually create the constraint system. So for each of these constraints here, we're going to make a set of vectors, a set of 3 vectors. So I'm going to put in brackets here a1, b1, and c1. Now a1 is a vector, and so is b1, and so is c1. In our example, we have 4 sets of 3 vectors, because we have 4 constraints. So how many entries does each of these vectors have? Well, this depends on our circuit. Specifically, how many different values are we expecting to see in our circuit. For example, here we're going to have 1 for all constant values. We'll have x, we'll have intermediate, intermediate 2, intermediate 3, and what we're calling the output value. So 6 items means our vectors have 6 entries. And for right now, let's just focus on the first constraint set of vectors so that we can cover the next steps. We're going to combine this triple of vectors with another vector. And we're going to do this by something called the dot product. And just quickly for the dot product, if I move this A vector over here and do a dot product with this, let's call it the solutions vector, the way you would actually read this is that you would do the first entries multiplied by each other. So this is 1 multiplied by A11. Then we're going to add x multiplied by A12. And we're going to go all the way down, adding in these 4 other multiples. And then we'll add it all together. And the actual output will be a single value. Now that you've seen how to do a dot product, we can show you the full equation. So we're going to have the solution vector dot product with the A vector, and remember this is just one value, and we'll multiply that by the solution vector dot product with the B vector, and our claim is that this product should equal the solutions vector dot product with the C vector. I said that we would just take the first constraint, this intermediate equals x multiplied by x. So if we have that, what are the values inside these A, B, and C vectors? Well, this is actually fairly straightforward to work out. Remember we said that the structure of this constraint was of the format y equals x operation z. And the operation is multiplication. But the x, and we're double using notation here because I'm speaking of those x's as if they're different things. But I just want you to think about the thing on the left of the operation. And here it's just x. So this means that in our dot product, we're going to want a 1 in line with the x. And everything else is 0 because there's nothing else on the left. And on the right hand side of the operation, we also just have a 1 in line with the x and nothing else. Then for the equals aspect, in the constraint it's on the left, in this solution equation it's on the right. We have one copy of int. We don't have int2 or int3 or anything else. So we're just going to want a 1 in line with the int. Now if we take the second constraint, int2 equals int multiplied by x. Well, the structure here is quite similar. So on the left hand side of the operation, we have one copy of int, so we put a 1 in line with the int. And on the right hand side, we just have an x again. Then on the equals side, we have one copy of int2. Then of course we'll do something similar for the third and fourth constraints. Now what about this thing I call the solution vector? I'm kind of hinting towards what it actually is. And it should be the solution. It should be a vector that satisfies every single one of these constraints. For example, we can just plug in some values now to make it satisfy constraint number 4, this out constraint. And if we put values in like so, we can do the dot product and add things together as I mentioned before, and we'll see that this instantiation of a vector does satisfy this constraint. But what about the other 3 constraints? Let's go and look at how this vector satisfies constraint 3. We'll do the dot products again and multiply them as the equation suggests. But then we see that we have 1 plus 2 multiplied by 1. Well, 1 plus 2 is 3, so 3 multiplied by 1. And then we say it equals 1. Well, actually, this obviously isn't satisfied. So this instantiation we had for the solutions vector is incorrect, and it won't pass all the checks. There will only be a few valid solution vectors. This is a cubic equation, so we should expect at most 3 possible solutions. These should be the only vectors to satisfy all of these constraints simultaneously. And this is what we're going to be proving knowledge of. You know, when you make a zero knowledge proof, you're saying you know all the values that satisfy every single one of these constraints. You knew some secret data and ran this computation. In general, you won't be able to guess what the values are. I mean, if you could, then you could break these systems. Here are the actual values in the solution vector. I mean, you could work this out yourself, of course, because this is quite a straightforward example, but in a more complex thing, it will take a bit longer. Let's zoom out here quickly. We had 4 constraints, and for each of those constraints, we have a triple of A, B, and C vectors. Everything we highlight in blue here is going to make up the public knowledge of this computation. These 4 sets of constraints represent the computation we're doing, and the value 35 is also going to be public data because you're saying this computation equals 35. And then the other items in this solution vector, these are the things we're going to hide. These are going to be the things that are the private data. It is the zero knowledge. In reality, you could also hide the value 35. But if you do that and you hide knowledge of the entire solution vector, you're just claiming you know some value that when you do x cubed plus x plus 5, it equals something. Now, saying you can plug any value into this computation is really not very useful. The power of the zero knowledge proofs come from combining public and private data. You know, you're saying that you know some value such that when you put it through a computation, you don't get some random value out. You specifically get out the value 35. And all the publicly viewable data here will be used to create the verifying key. And for provers, they're also going to take the hidden data, what's covered in this solutions vector here, and they'll use that to also build their proving key. So everybody should know the verifying key so that they can check a proof, but only the prover should know the proving key because it contains the secret data. So far we've seen how to take our equation, flatten it into its fundamental steps, turn those steps into a constraint system, and the next stuff we have to see is how to commit to this data in a way that's going to let us prove certain properties about it. For that, we're now going to turn to Lagrange Interpolation. The purpose of this is to commit to values. We want to commit to some values such that we can't later change these values and claim they're the things we committed to. Neither do we want these commitments to reveal anything about the data we committed to. So for the Lagrange interpolation, I want to take a 2D plane, and we're only really interested right now in the values between 1 and 4. So let's imagine that we wanted to commit to 4 values, 1, 3, 5, and 1. We can imagine this as committing to some function that evaluates to 1 at x equals 1, and evaluates to 3 at x equals 2, evaluates to 5 at x equals 3, and evaluates to 1 again at x equals 4. We're going to do this with things we call Lagrange polynomials. A Lagrange polynomial at position 1 is a function that takes the value 1 at x equals 1, and it takes the value 0 for all the other points in the domain we care about, which for right now our domain is 1, 2, 3, and 4. Now the special thing is this polynomial is the unique degree 3 polynomial that satisfies those conditions. Because the space we're interested in contains 4 points, our Lagrange polynomials are of degree 3. So our second Lagrange polynomial takes the value 1 at x equals 2, and it takes the value 0 for x equals 1, 3, or 4. Now on the right here I do this L2 of x, that's our shorthand notation for Lagrange polynomial 2, and above that we have the coefficient form. Now if I want to commit to this vector that takes value 3 at x equals 2, all I need to do is take 3 copies of this Lagrange polynomial. So 3 multiplied by L2 of x. Similarly, for the third Lagrange polynomial, I'm going to want 5 copies of that. And of the fourth polynomial, I just want 1 copy. Then if we add these copies of the Lagrange polynomials together, what we will get out is the unique degree 3 polynomial that passes through all the values we care about in our domain. So that was a quick interlude about how the Lagrange interpolation works. So we now know that we can commit to vectors of numbers. And how are we going to apply this to the constraints we already have? Well, what we want to do here are our 4 constraints in their triplets of vectors. I want to take the first vector from each of these triples, so the A vector in each case, and put them together like this. Then I just want to focus on the first entry in each of these vectors. We'll pull them down to the same position to indicate that we're going to commit to them, and we're going to do this Lagrange interpolation again. So we have the first Lagrange polynomial. Well, at x equals 1, we just want the value 0, so we don't need any copies of L1. Similarly, for L2 and L3, we don't need any copies of those. But for L4, we need 5 copies. So 5 multiplied by L4 of x is going to be the interpolation of this vector. It's going to be our commitment to it. Now we can do this commitment to all of the entries in these vectors. So we did the first row, then we can do the next 5 rows using the same basis. And I put the Lagrange polynomials above to remind you of how we're doing this. We can write this in Lagrange form or also coefficient form, but we want to write it most compactly as just ai of x so that we can write it down more easily. I quickly want to remind ourselves of how we got here. These 4 vectors came from each of their constraints, and these constraint vectors were representations of the actual steps, and the steps was just a breakdown of this starting computation. So going through that again, we have our starting computation that we flatten into its fundamental steps. We then turn these fundamental steps into the constraint vectors, where we populate these vectors based on the assignment in the potential solution vector. Then we align these vectors together such that we have the A vectors, the B vectors, and the C vectors. Then once the vectors are arranged like this in the A vectors, B vectors, and C vectors, we want to commit to each line, do a Lagrange interpolation on each line to commit to the values. Now we saw that done for the A vectors, where we got all the ai of x. Then we want to do the same for all the B and C vectors, generating 12 more constraint polynomials. Now that we have these constraint polynomials, we can put them back into this solution equation with these dot products. I just want to rearrange the equation here to move everything onto the left-hand side of the equal sign. The reason for this is that we want to have something equals 0. Now more specifically, it's actually going to be something equals 0 for all x in the domain that we care about. And remember previously that we just had separate constraints in this format. But now that we committed to the rows, we kind of have every single constraint represented here in the A's, B's, and C's polynomials. You know, if we evaluate these polynomials at 1, well, what we'll get out will actually be the first constraint vector. Similarly, if we evaluate it at 2, we'll get out the second constraint vector, the int 2 equals int multiplied by x. And similar for the third and fourth constraint vectors. You see that we've now kind of combined our information together to simultaneously check every single constraint in one go. We're back at this solution equation now, but instead of the separate constraints, we actually have the constraint commitments, which are these general polynomials a of x, b of x, and c of x. Just a quick reminder of how the dot product works. Now we're actually summing all the constraints together. So we'll have 1 multiplied by a1 of x plus x multiplied by a2 of x, and so on and so forth. And what this gives us is another equation, call it just a of x, that somehow compresses all those constraints alongside the solution vector into a single, more checkable entity. So we can do this with the other constraints as well and get back a of x multiplied by b of x minus c of x equals 0. But more specifically, it equals 0 for all x in 1 to 4. So if x is 1, 2, 3, or 4. Now comes an important claim. We say this is true if and only if a of x multiplied by b of x minus c of x equals h multiplied by z of x. Now z of x here is what we call the vanishing polynomial. It is 0 on all the values in the domain that we care about. It's 0 at 1, 2, 3, and 4. That's why we have this representation, z of x equals x minus 1, x minus 2, x minus 3, x minus 4. You should see that if you plug in any of the values in our domain, z of x should equal 0. And there's actually a more important fact of algebra here, and this is that any polynomial that is 0 on the same domain must be divisible by this vanishing polynomial. So this h that's next to the z of x in this if and only if, the h is just arbitrary. We're saying that it actually satisfies this equation. Because we know if the stuff on the left-hand side is 0 in those 4 points of our domain, then maths tells us that it must be divisible by the vanishing polynomial. And actually, this is the specific thing that we're going to want to check. This stuff on the left-hand side of the equals sign, we actually want to prove that it is divisible by the vanishing polynomial z of x. If it's not divisible by z of x, then you won't get out a polynomial in the division. You'll get out a rational function. And this means you won't be able to complete the proof. And this is the core idea we want to check in the end. I know that was a lot, and actually we didn't even cover everything we wanted to within an R1CS system. Even the stuff we showed you was quite limited in terms of the depth. And this is why we really want to make more videos in the future to go over these in much more detail so that you can start to put a picture together. But hopefully you did learn something about how an R1CS system works and some of the core ideas. If you have any questions or want to discuss things further, you can check out our Discord, and we have some conversations going on there. Feel free to ask anything you want. In particular, we'd be very interested to hear if you have any recommendations about how we could change the style of the video or what else we could talk about that you think would really benefit your learning. See you next time.